Okay, welcome. This is our fourth lecture in the series of 6 lectures in our Basin and Petroleum System Modeling Industrial Affiliates program on the use of petroleum geochemistry in basin modeling. And I'm Ken Peters, and I'm a co-principal in that program. These lectures are designed for our BPSM PhD candidates, but we're also releasing these to our industrial affiliates because we believe those will be useful to them. What I'd like to do today is talk a little bit about geochemical correlation. We just finished up a section on kinetics. We're going to do some geochemical correlation. This is very important. I think a lot of basin modelers don't think too much about that. You got to be very careful because if you're not certain of the source rocks in your basin, you're going to be assigning characteristics to rocks that maybe are not actually the source of the oil and the gas. And I've actually seen papers that are like this. They missed a source rock or missed more than one source rock, or they got the source rock wrong. And the model then is certainly not useful. So what we want to do is give you a background in how this correlation is done. This is to establish a petroleum system. You need to establish the petroleum system using geochemical correlation of the petroleum, which may have migrated a great distance, to that pod of active source rock somewhere else in the basin. Now, I want to introduce this discussion with a little talk about API gravity and gas to oil ratio. These are sort of bulk parameters, as is sulfur content, and there are other things you can think of that are bulk parameters. It's not a good idea to try to correlate crude oils as to their origin with bulk parameters, right? I mean, it's dangerous, especially with things like API gravity and Geor that are affected by so many secondary processes. Biodegradation, for example, can really change the API gravity of a crude oil. And of course, API gravity is inversely related to the specific gravity. Gravity of 10 is the same basically as water. Oils that have lower API gravities will sink. And some places in the world, you actually find oil in synclines, believe it or not, where the interstices are, between the sand grains are actually above the water table. So the oil sinks to the bottom. Those are pretty rare, but you can see here the range and characteristics of these types of oils. Condensates, typically 45 degrees gravity or more. Okay, well, we also look at Geor. Here's a table of data that I put together from the Gulf of Mexico. And it's kind of interesting. You can see here our reservoir temperature. And these are the equivalent vitrinite reflectance. Again, we talked about vitrinite reflectance. These are the equivalent vitrinite reflectance maturation at that level in the basin. And you see we have here the fraction of oil cracked. All right, so this is a transformation ratio basically. And here we have gas to oil ratio. And here we have API gravity. You can see the gas wetness as well. API gravity is going up here. And actually it drops right there at the very high temperature end. And that's because of the diamondoids that we talked about a little bit earlier in the first lecture. The concentration of diamondoids is probably high in this particular oil. So it's pure methane plus adamantane in there as well. Typically, gas to oil ratios are standard cubic feet per barrel. Black oil, the GOR is less than about 2,000. Volatile oils, it's from 2,000 to say 3,000. And gas oil ratio is greater than 3,000 standard cubic feet per barrel. We would call those condensates. That's a very simple description, and there are some discrepancies in the literature about where those dividing lines occur, but they're descriptive, and as long as you define what you're saying, that's okay. So let's look at GOR. GOR is, again, very difficult to predict because of all the things that can affect it. But here's a paper by Fred Mango and Dan Jarvie where they actually used some C5 to C7 hydrocarbons to predict with reasonable accuracy here to predict the GOR of the associated fluids. You can do the same thing with isotopes. There are isotope approaches. This is Kevin Fairwarn. Geomark had a little meeting where they talked about these things back in 2013, and this is excerpted from that. You can see the GOR forms a nice relationship with the equivalent vitronite reflectance based on gas isotopes. Now, recently, there was a very good paper by Friedman and Baur in 2019, where he actually developed a means of a basin modeling approach to predicting API gravity. Most predictions of oil API gravity from basin models really show a pretty poor match with field observations because the models really do not predict increasing API with increasing maturity. So Friedman developed this module, and I'm going to tell you about it in the next 3 slides. It is now in the latest version of Petromod, and I'm sure other people will include versions of Friedman's work in their models as well. It predicts oil API gravity based on source rock kinetic models, and here are the ones that he did the work with. He took the Pepper and Corvey organophases models. We talked about these a little bit in the kinetics section. And again, I would say, yeah, if you can avoid using default kinetics like this or kinetics based on depositional environment, do so, measure your own kinetics. But a lot of times you're forced to use, say, a type B here. That's a marine, algal, and bacterial type. It's the same as the IFP, Institute Français de Pétrole, type 2 kerogen. Okay? And there are kinetics associated with those that I'm not showing here, but each of these has its own kinetics. And now what Friedman did is he wanted to predict API gravity. So his model, it's a kinetic model, source rock model. It uses these kinetics. And what he did is he employed 2 liquid components of different densities that are generated from and expelled from the source rock during the calculation and undergo relative mixing during maturation. So he created 5 new kinetic data sets from the original organophases models of Pepper and Corvey, and these yield actually geologically reasonable API gravity trends. And he also has some additional calculations in there on source rock sorption and secondary cracking schemes that modify the primary generated API gravity trends. So let's look at what kind of ranges of API gravity he decided were appropriate for his models. This is from his 2019 paper, which I think is one of the better papers I've seen in recent years. It's really quite compelling, and it shows here the sort of representative ranges of API gravity that you see for these different types of Pepper and Corvey organophases. The references for each source rock are displayed at the right, and these are references that talk about the API gravity. These default ranges of API gravity for the 5 new kinetic models represent observed sort of averages, but in his module in Petromod, these can be modified easily. These can be adjusted. So here's just one example. This is one of those 5 modified kinetic models. And you assume you have a 1D model. This shows then for that 1D model, assuming type B, Pepper and Corvey type B, that's a type 2 kerogen at that 1D model location, you can model the instantaneous expelled API gravity. And you can see it ranges here from 20 to 70. And the API, here's the transformation ratio that we talked about in the kinetics section earlier. That's that sigmoidal curve as a function of time, right, in this particular location. And then we've got the calculation, the predicted API gravity through time in this model. And here's the predicted GOR listed over here in red. Okay? So you can see the cumulative mass fractions expelled from this source rock, this type 2 or type B source rock, considering sorption and in source rock secondary cracking processes, they're about 27% gas and about 73% oil. Okay, so once again, I've discussed these API gravity and Geor, even though we really don't use them for correlation. It's mainly to emphasize that, yeah, don't use them for correlation because they're so readily altered. But of course, they're important to try to predict. And I think this is a new approach that seems to work quite well. So what I want to do now is I want to talk about geochemical correlation. And we talked about vitronite reflectance and Rocky-Val. Those are sort of workhorses for screening, rapid screening of rock samples and oil samples. Well, gas chromatograms are a quick way to look at the character of oil and gas. And so this is created by a gas chromatograph. The chromatograph separates complex mixtures. I'm showing you here the way it works. Most people, I think, understand this. You inject a sample or a saturate fraction or an aromatic fraction, and it moves down this column, which is many, many meters long. A typical capillary column is 60 or more meters in length. And that's because we want the molecules in the material we inject to interact between the mobile and the stationary phase. The mobile phase is usually some carrier gas like helium, and then the stationary phase is some polymeric material, and the organic materials, the compounds, as they go through, will jump between those two phases. Some compounds don't like the stationary phase and they move through the mobile phase quickly, and some are slower. They spend more time adsorbed to the stationary phase. Some tend to stick up here. The heavier compounds tend to stick at the head of the column, and that's why these gas chromatograms are all heated. They have an oven, so the temperature can be raised at a programmed rate, and we can get most of the compounds to travel through. Of course, you normally don't inject black oil into this because the asphaltenes would tend to gum up the column. So those samples are usually de-asphaltened using a prep column before that's done. Yeah, for detection, there are lots of different detectors, but probably the most common is the selective detector, the flame ionization detector, and it's going to measure what you actually burn. So here comes your carrier gas, nitrogen or helium, and it's carrying compounds with it. And you mix that with a little hydrogen, and you have a flame jet electrode here. You're burning those peaks as they come through. This is a selective detector because you're not going to see CO2. You won't see it because it doesn't burn, right? But a hydrocarbon like methane will burn, and you can measure that with your electrode. Now, FIDs have extremely dynamic ranges. They're very, very useful and very powerful for in terms of a broad dynamic range where they can make good measurements of compounds. So you can generate what's called a gas chromatogram, and I'm sure most of you have seen gas chromatograms before. This is a chromatogram of an oil it happens to be from Northwest India, okay? But it's an oil. Here's the injection, and then time is going to the right, and we have all these peaks, and you can see these homologous series that we talked about a little bit in the first lecture. Here's NC15. Those are carbon atoms with the appropriate number of hydrogens on them, right? So that's got 15 carbon atoms in a row. That's the normal C15, C16, there's C17, C18, C19, 20, 21, 22, 23, and so forth. This chromatogram is interesting because it has also another homologous series here that's pretty evident there. This second part of that doublet there is pristane, and this one is phytane. And we talked about phytane. It comes from the side chain in chlorophyll, and that's why pristane and phytane are so big. pristane lacks this terminal carbon here, so it's basically the same backbone structure. There's a whole homologous series of those, but these two are the biggest because the vital side chain of chlorophyll is 20 carbon atoms long. This also has a rising baseline, which can result from a couple of things. It could be low maturity. It could be some biodegradation, and you have a mixed oil here with a less mature oil because the N-alkanes are attacked readily during biodegradation. In this particular case, it's a fairly low maturity oil, and I know that from the biomarker analysis. So let's look at a few GCs. Here's some GCs from different parts of the world. This one we call a nice waxy crude oil. We've got some internal standards here that I've circled to help us figure out where we are. There's the pristane and the phytane. Notice the ratio of pristane to phytane. Yeah, and there's a peak here you can actually see. It's big enough. You can see it's called boturococcane. That's a classic biomarker that comes from Boturococcus, which is a lacustrine alga. We know that this oil came from a lacustrine source rock. And look at the big paraffin peaks, the big N-alkane peaks, lots of them. And we would describe this as a waxy crude oil. Here's another one from Prinos, Greece, and it's kind of unusual. It's got a very low pristane to phytane ratio, and it has a strong, even numbered predominance. Let's see if I'm looking at that right here. Yeah, it looks like C16, C17, C18, C19, C20. You see there's a strong even carbon number predominance in the N-alkane series, and that generally means anoxia, as does the low pristane to phytane ratio. Here's another very unusual oil from Iowa, Central North America. It basically lacks pristane and phytane, and it's got a really pronounced odd to even preference in the alkanes. This essentially came from one organism. It's almost a monoculture in that marine environment. It was called Gliocephalomorpha prisca. So you can tell a lot by looking at the GC flame ionization detector traces, or the GC traces, just from the character of the oil, as long as it's not biodegraded. Here are three oils that we know are genetically related, but you can see what's happening to the oils. They're being biodegraded. This oil is a little shallower than the others, and there's been access to the oil by aerobic microbes, and they've attacked and destroyed virtually all of the alkanes. You see the rising UCM here, the unresolved complex mixture. The same oil, basically, a little deeper in the section. The UCM is not as large. These are unresolved complex compounds, mostly naphthenic type compounds that are resistant to biodegradation. We still see now pristane and phytane in this oil. They're a little more resistant than the N-alkanes. And here's the pristine oil without having been biodegraded. You can see the pristane to phytane ratio is greater than 1. And we've got these normal alkanes that are basically missing in this oil, and pristane and phytane are still there, but now even pristane and phytane are gone. So yeah, biodegradation makes correlating oils a little more difficult. Here's another example of some gas chromatograms. These two oils are also genetically identical. They came from the same source rock in Wyoming. But this one, the lower one here, is a little more mature. It's thermally more mature than this one. How do I know that? Well, I look at biomarker stereoisomer ratios, and I can see this one is clearly more mature. It's preferentially, it's cracked basically these higher molecular weight components, and the whole chromatogram is shifted to lower molecular weight because everything is being cracked toward a methane composition eventually. So you can still see pristane and phytane in both of these oils, but this one is more mature. This has a bimodal distribution of N-alkanes, which is also an interesting thing we can talk about at some point. So this is Alfred Tribes, and I want to introduce biomarkers to you. I've already talked a little bit about pristane and phytane a couple of times, and I also talked in our first lecture about deoxyphylloerythroidioporphyrin. This is a porphyrin. So here we have chlorophyll in a green plant. or algae. There are lots of different types of chlorophylls, but you can see chlorophyll is a tetrapyrrole, nitrogens, and it's got a magnesium, and it's got a side chain that comes off here with an ester group, and attached to that ester group is this isoprenoid, and we call that the phytol side chain in chlorophyll. And so pristane and phytane, you can see where they're coming from. There's a lot of chlorophyll in plants when they're deposited in sediments, and some of it gets preserved in the source rock and eventually ends up in the oil, and that's the pristane and the phytane. See, pristane has one less carbon atom, so that's C19 in that homologous series. This is the next homolog in the series, C20. So you see here the some of the porphyrins that you can get, and I'm just showing a couple of them here. And normally the magnesium during diagenesis is replaced by something like nickel or vanadium or chromium or some other metal, usually vanadium or nickel. So actually Alfred Tribes was the first to recognize this, and a lot of people consider him the father of petroleum or organic geochemistry. So let's look a little bit, a very simple example of what happens to the side chain in chlorophyll during burial under oxic conditions. Remember, we talked about the difference in redox between preservation under oxic versus anoxic conditions. These are oxic conditions. You can see the water column has a lot of oxygen in it. That organic matter is going to be through the guts of different organisms here. And then when it gets to the sediments, it's still going to be the food for different organisms, burrowing worms and so forth, until it finally gets buried deeply enough to get into the sulfate reducing zone. Okay, so you start off with phytol, which is broken off now from that side chain in chlorophyll. It's an alcohol with a double bond in it here, and you can see that can be oxidized to a carboxyl group, which then breaks off as carbon dioxide. So we've lost that terminal carbon. So we went from a C20 side chain here to a C19 pristine that has a double bond. And of course, once it gets into this reducing setting, that double bond will be reduced. It'll pick up hydrogen. And so we've ended up with one less carbon atom. We go from C19 here down to C20 here down to C19 here in pristine. Something different happens under reducing conditions. Here are the anoxic, here's an anoxic example, oxic water column, but once the organic matter gets down into the water column that's still, that's anoxic, and the sediments that are anoxic, then what happens is there's not enough oxygen around. That hydroxyl group just basically is broken off during diagenesis, and you preserve that terminal carbon. So you go from C20 to C20, and that's phytane. Yep, so the pristane to phytane ratio is a very simple tool that people have used. Dydick published an early paper on it with some controversy about what the cutoffs were for defining oxic versus anoxic. It's a little fuzzy there, but basically this is a very useful tool. You can actually look at a chromatogram and look at the pristane to phytane ratio, and unless the oil has been biodegraded, you can generally say something about the depositional environment of the source rock from the composition of the oil. So here's one way of doing that. Remember, pristane comes out just after the NC17, and phytane just comes out just after the NC18 on the gas chromatograms. You can just measure those peak heights or their areas, take the ratio and plot them on this sort of a diagram. And here you can see we have values along this sort of range here. That's going to be reducing. Low pristane, that's going to be high phytane relative to pristane. So low pristane to phytane ratios. Yeah, here's one group of oil samples, and they're sort of all falling along this trend, a very reducing trend. Now you can stretch these out a little bit. Oils that will stretch out on this trend a little bit because of maturity or because of biodegradation. Biodegradation, for example, will move you up this way because the alkane is more readily degraded than the isoprenoid. Those branches are much more difficult to digest by an organism than the straight chain alkane. Likewise, up here, you've got another group of oils that are different than these, and you can say, well, these probably came from a terrigenous type 3 source rock, whereas these came from a more marine reducing anoxic source rock. Yeah, of course, you want to always confirm this. You don't trust anybody. You always want to confirm this preliminary evidence from the simple measurements with other measurements that you can make. So here's a paper that Moses Chung came out with in 1992. I used to work with Moses when he was at Mobil Oil Company. And this shows the carbon isotope ratio of oil versus that pristine to phytane ratio. And he put this together. And I think, yeah, he's assigned some sort of rough divisions here for what kind of oil you've got in terms of geologic age. For example, the Miocene carbon isotope values were unusually heavy for many Miocene oils, and they're unusually negative for Paleozoic or Precambrian oils, and sulfur content affects this. The more sulfur you have in oil, likely the more reducing the conditions and the lower the pristine to phytane ratio. But this chart just by itself is something that's useful for correlation. If you've got two samples that plot right on top of each other, it's like right there and there, yeah, I mean, I would say there's some evidence that they might be from the same source. Of course, with only two parameters, there's always the possibility that those samples are from opposite sides of the planet. But that's preliminary evidence that there might be a genetic relationship. And these are easy parameters to determine. Pristine phytane, straight off a gas chromatogram. And the carbon isotope ratio for the oil is something that's relatively easy to measure as well. Again, there are pitfalls you've got to watch out for biodegradation and other things, but that's one of the charts that you could use to help make you feel better about the correlation between the oils that you are looking at. So let's talk a little bit about reservoir geochemistry. I know this is not directly related to our exploration, but there's a lot of reservoir geochemistry that is done because it offers benefits, defining compartments, reservoir compartments. You can use it to optimize steam flooding, eliminate unnecessary drill stem tests, identify gas oil and oil water contacts or leaky casing, contamination. You can quantify contributions from multiple zones through time. So this helps to resolve production disputes. And I'll show you an example a little later of a mixing, how you can deconvolute some mixtures that might occur. It's fast because it involves gas chromatography. It's fairly inexpensive. GC doesn't cost much to run. And it complements other tools. And you can look at extracts from sidewall cores and cuttings and bottles and commingled oils to define whether these oils are actually different and are separated somehow in different compartments. So oil reservoir continuity has been around a long time. The pioneer in that work was Chevron in the very early days. Chevron had some of the first gas chromatographs that were made available. And I remember we used to pack those gas chromatographs columns ourselves. We look at interparaffin peaks, that is peaks between the big alkane peaks, and we number them, and they're measured using standardized baselines. In the old days, they used to actually draw the baselines themselves, and then measure the peak heights or the areas, not the absolute amounts, right? So if you could measure peak heights, you could do it with a ruler. More recently, of course, these are done in an automated fashion, either area or peak heights. And it's your decision which way to go. Peak heights are generally fine if the resolution is good. You've got nice narrow peaks with no tailing. Selected peaks best separate the groups that make geologic and engineering sense. So you're looking for differences in the chromatograms. If you've got two oils, you want to look at the differences in them, and you'll search that chromatogram and try to find the same peaks, but differences in the ratios between those peaks and the adjacent peaks. Okay, so the peaks that you end up choosing may vary between studies. The ratios are calculated from adjacent or closely spaced peaks, right? You want them to have similar chemistry and respond to secondary factors, secondary processes in similar ways. And you don't add any weight to any given ratio. Well, here's a nice, this is a nice chromatogram, C7 hydrocarbon analysis, baseline resolution there, and no real tailing on the peaks. This is the solvent peak here. And you've got very nice identification of the compounds. They're easy to identify using basically tables of retention time. And so you can start looking at ratios. Here's an internal standard. There's the normal NC7, and you can take ratios of some of these peaks. Now, most of the work that's done is done with compounds in the range of at least C5 to C15 plus. Okay, so here is Sable Island. This is some work that is described in the Biomarker guide. And there's so many samples on here, we've actually color-coded a whole swath of samples. Here are the red ones. You can see the red ones over here. These are all samples from different depths in that Sable Island well. And each of these ratios then, they're plotted out from an origin, okay? These are called Halpern ratios after Henry Halpern, who was with Saudi Aramco for a long time. And this then is very useful to define different groups. The numbers at the end of each axis are the endpoints for individual ratios. And two end member oils are apparent. You can see there are two end members here, the red ones and the purple ones, and the green ones look like they're probably mixtures of those two oil families. So there's a lot that can be learned using this approach. That's called a star diagram that I just showed you. Star diagrams or polar plots, yeah, they can result from different reasons. And in most cases, the interpreter doesn't really care what the reasons are. They're simply interested in differentiating different oil types in different parts of the reservoir. They want to know whether the reservoir is continuous or whether they're separate reservoirs. So their possible reasons for differences are listed here. Samples originated from different source rocks. Yeah, they're going to look different. Samples are from the same source rock but achieved different thermal maturity, right, before they were emplaced. The samples had different reservoir filling histories. The samples underwent different secondary processes in the reservoir after emplacement. So if there are just very slight differences in water washing, say, or biodegradation on two different sides of a sealing fault, you will see those differences. You'll be able to see those in the chromatograms if you look carefully enough at the chromatograms. So for oil fingerprinting, here's some rules of thumb. Generally C7 to C25. Interparaffin, not the paraffins, not the alkanes, but the other peaks between are best to define the compartments. Watch out for the lighter compounds because you can lose those during sample handling. And that's one reason why we use adjacent peaks. You don't want to ratio a really light compound to a much heavier compound because that light compound might be preferentially lost in some of your samples. The repeatability here is on the order of 1 to 3%. That's some of the work that Russ Kaufman did at Chevron in the 1980s and 90s. Data for all samples is best obtained using the same instrument and conditions. Preferably you run the samples back to back or close in time to each other because, of course, columns gradually degrade through time, chromatographic columns. If the ratios differ only in a narrow range rather than throughout the chromatogram, then you need to worry about contamination. You might have, for example, some diesel that was added to one sample and not to another one. That diesel will show up in a specific range of molecular weight. More differing ratios yield greater confidence in the compartments. Polar plots are used to compare usually no more than about 12 samples. Once you get more than about a dozen samples, it really becomes difficult to see to figure out what you're seeing. So you really want to use chemometrics. We call it chemometrics for large data sets. Things like hierarchical cluster analysis or principal component analysis. We'll talk a little bit about those later. Those are very powerful tools. And when you get large data sets, they're indispensable. Well, let's look at an example, really quick example of production issue. This is Russ Kaufman's work. This is in the Gulf of Mexico, and you can see we've got a dual producing well here with 2 drill strings. And that well was completed in 1967. And you see you've got a shallow end member, 7,000 feet, and you've got it packed off, and you've got oil also being produced from the 7,800 foot sand. Okay, so these are distinct oils. They're probably from the same source. The differences are minor, but we can tell the differences on the gas chromatograms if we look closely enough, because the FID is so sensitive. So in 1967, they collected samples from those 2 strings, and then through time, they were collecting samples through time and storing them in a storage shed. That's good. So later, during the production from these wells, they started noticing some anomalies in the production, and they suspected there might be a leak, but they weren't sure. So what Russ did was kind of neat. He went to the lab and he went to the storage shed, and he got samples from these 2 units through time. And then in the laboratory, he mixed those in various proportions, of course, weighing them very carefully. He mixed them in various proportions. And then he went to his capillary gas chromatography, and he looked at those mixtures. So for example, here is 100% from that 7,800 foot sand. That's the long string. And he looked, I'm just showing you 3 ratios here. I usually used about 16 different ratios. So this is the peak number on the chromatogram. You know, these capillary chromatograms have literally hundreds or even thousands of peaks that are suitable. So here's 86 to 85. And in 1967, yeah, it plots right there. And right, then he's mixing that 7,800 foot end member with the other end member, the 7,000 foot end member. And so 100% of that ratio is different. The 86 to 85 is over here. And then of course he made a 50-50 mixture, and he made a 75-25 and a 25-75 mixture. So now he has a calibration line, and he's using ratios now. I gotta warn you about ratios. Ratios will not mix linearly unless the denominator is the same, okay? If the denominator differs, then you're going to mix as a curve. So these are ratios, basically ppm type ratios. So you're mixing linearly, and you have different calibrations for each ratio that you look at. So here are 3 ratios and 3 different calibrations. 1972, they went to the storage shed, and gee, it looks like the 1972 oil that's produced from a long string is the same as that from 1967, no problem. 1981, though, it plots here. So the long string is being contaminated by short string oil. There's a leak in the system. Something is broken in that long string. And by 1983, it's getting worse. And I could show you other samples from later on. It gets literally all the oil is coming from the short string. Okay, well, it turns out there's, this approach is really obsolete now. It's tedious, it takes time. You got to weigh the samples carefully and do replicates. Now we can deconvolute mixtures using some chemometrics, alternating least squares, or similar methods, provided that one considers concentrations and not ratios. Okay, so here's some quick conclusions now on oil fingerprinting and reservoir compartments, rapid screening tools for crude oil, GC, API gravity, metal content, sulfur content, carbon isotopes. Watch out for API gravity and even sulfur content and carbon isotopes. Just by themselves, they can get you in trouble, especially things like API gravity and sulfur content, because the secondary processes really affect those. GC, yeah, it's good to look at. GC can be used to infer kerogen type. We showed the example of pristane to phytane. It indicates oxicity of the source rock setting. GCs of related oils can differ due to secondary processes. GC peaks and Malcolm software can be used for correlation and production allocation. Malcolm is a Schlumberger product. The ratios give nonlinear mixing curves, and I'll talk more about that in a little bit. Adjacent, C7 to C25 interparaffin GC peaks are best. Yep, to define compartments. GC data for all samples must be obtained using the same instrument and conditions, preferably doing those analyses within a few days of each other or back to back. Reservoir continuity doesn't really apply to tight reservoir rock. You know, when you're talking about unconventionals, that doesn't really apply. So GC and isotopes complement pressure, water, and residual salt data to define compartments. People use pressure curves sometimes to define compartments. It's good to use both GC and pressure curves to define those compartments because both techniques can fail. And it's good to double check. Okay, so here's some references on that for oil fingerprinting, production allocation. There are a number of papers in here you might want to look at. McCaffrey, Mark McCaffrey here from 2011, a nice paper on that. And also I have a paper in 2008 that talks about deconvoluting mixed oils. We'll talk a little bit more about that later. And the older Chevron work, Rong Wang, Dave Baskin, Russ Kaufman. There's some classic papers there that describe that older work. Let's talk about isotopes. Now, isotopes, stable carbon isotopes are useful. Of course, carbon-14 is not stable. It has a half-life of about 5,270 years. So it's gone by the time you have petroleum. But carbon-13 and carbon-12 are quite stable. You can see carbon-13 is only about 1% of all carbon. The rest is pretty much carbon-12. 6 protons and 6 neutrons. This has a C13, an extra C13, an extra neutron. So it's going to be C13 rich. And the original standard was the PD belemnite. It was a little marine organism here that had a carbonate test. And of course, that was used up a long time ago, but there are other standards that people use. PD belemnite is the standard that everybody relates to when they measure carbon isotope values. And of course, carbon combines with 4 valence electrons. It likes to form 4 bonds. But what makes the difference in the bonding is the outer shells. The difference here is in mass of the main mass is different here. This one's a little bit heavier than that one because it's got that extra neutron. So those two isotopes react at a little bit different rates. And so we have a kinetic isotope effect and an equilibrium isotope effect that can affect those isotope compositions. Isotopes are defined using the delta notation. So delta in parts per mil, that's per thousand, is 1,000 times the R value, say C13 to C12 for the sample minus the standard, divided by the standard. Well, we do that so that isotope values are, you can describe them in simple terms. So here are some isotope values. Yeah, most organic matter is going to be quite negative compared to the standard. PD belemnite standard is defined as 0 on the PDB scale. Marine carbonate minerals, yeah. And organic matter has these isotopic fractionations associated with fixing the carbon. We talked about photosynthesis and fixing carbon, marine plants and plankton. You see there's isotopic fractionation, and the plants, the fractionation actually favors the light isotope. So you end up with a negative value in the organic matter, different types of plants. And of course, oils fall in this range. I'll show you I'll blow this range up. We can measure isotope values quite accurately. And here's what microbial gas looks like. We'll talk about biogenic gas generation in the next lecture. And there's really quite strong isotope fractionations when the methanogens make methane. So let's look at oils now. This is a blow up of that, and we can measure isotope values plus or minus 0.1 part per thousand, or PdB. And here's some examples of isotope compositions of crude oils from around the world. You can see there actually is a temporal trend here. These are older oils. They're more negative. Ordovician, lower Paleozoic or Precambrian oils are commonly minus 30, minus 35. And as you come up this trend here, you're going Phosphoria, yeah, Kimmeridge, yeah, this is Permian, Jurassic, Cretaceous. Monterey, of course, is Miocene, and it's isotopically enriched in carbon-13. So there's a temporal or secular variation in isotope composition. Unfortunately, this is not sharp enough to really be useful to define the age of the source rock, but it can help. If you have an isotope value way down here, minus 30, 35, it's probably a very old oil. And if you have one that's up about minus 25, minus 20, it's probably a tertiary and even a Miocene oil. Now, there are various isotope methods that are used. This is the Galimov plot, the Galimov type curve. You can fractionate. We talked about fractionating oil. You take a whole oil and fractionate it into saturates, aromatics, NSOs or resins, and asphaltenes, and you can create this Galimov type curve. The pink area here shows the isotope ranges for these different components: whole oil, bitumen from rock, and kerogen. This orange, this color here shows you how most of the oils, the Jurassic oils in West Siberia, plot. And here's an oil right here, this Coglum 31. It's right in there. So we would say that that's based on the isotope type curve. It's probably a Bajanov Upper Jurassic oil. You can even do some oil to source rock correlation, although it gets a little bit dicey. Here, for example, the bitumen from this rock, this Pokachev, looks like it fits a Jurassic source, but notice the isotope composition is a little bit off that trend. You'd expect it over here somewhere. Well, with kerogen, you have the reactive kerogen, but you also have the inert kerogen, which has sometimes its own isotope composition. I will say that this Pokachev is almost certainly from this extract is almost certainly going to match up with these oils. That's the source. It's a Upper Jurassic source. Over here, we've got an oil from the Yemyegov, or actually a kerogen from Yemyegov. That's clearly not related. That's a different source. So the Galimov type curve is useful. You may see that. You probably will also see this kind of plot used for oil correlation. This is called a Sofer plot after Svi Sofer. And what he did is he looked at about 550 worldwide oils, and he plotted up the saturate versus the aromatic carbon isotope value. And he found that they split out along sort of this line. Up here, we have terrigenous oils. Down here, we have mostly marine oils. And what I've shown on this figure is just some oils from the San Joaquin Basin in California. You can see the isotopes of the saturates and the aromatics really nicely split out these oils. These are the Miocene oils. Remember, I said those were isotopically heavy or enriched in C13. And then we've got these more negative Eocene oils, the Cranehagen oils. And we can even look here and get some Eocene Toomey oil. So Toomey is a little bit younger than the Cranehagen, but it's still Eocene. And so we can say most of these oils were marine, and we've got the beginnings of an oil source rock correlation here. This is actually from a paper by Lillis and Magoon in 2008, and here's another one from myself in 1994, same sort of thing. In this basin, the isotope compositions of the oils are, from the different source rocks, are quite distinct. In other basins, not so. You may have oils that are quite different in age that have similar isotope compositions. Sofer defined the canonical variable. You can calculate it this way, and the canonical variable is another parameter that is related to this terrigenous versus marine. Basically, the canonical variable is the orthogonal distance from this best fit line. Okay, so that commonly corresponds with wax content from the gas chromatogram. Lots of N-alkanes, it's probably terrigenous. Less N-alkanes, it's probably a marine source rock. Now we can get sophisticated with isotopes, and I'm just going to describe a couple very quick examples here. This is isotope ratio monitoring, gas chromatography, mass spectrometry. Now instead of a flame ionization detector, we're using a mass spectrometer, okay? So we take the peaks as they come out at the end of the gas chromatograph here and combust them, and then we measure the isotope composition of the CO2 for each peak. So we, there have been some pretty sophisticated studies here. I'm just going to show you one here. This is from the Jurassic in the Middle East. You can see these are Jurassic oils. These are nice black oils. And these are the diamondoids. I introduced the adamantane to you in the first lecture. That's that little ball here. Very thermally stable compound. It's present even in gas condensates. And these Silurian oils from below the salt in the Middle East are very light oils, low sulfur, light oils. These Jurassic oils are higher sulfur. They look very different, and it's tough to identify mixtures. But here's a beautiful example of a mixture right here. This oil with the yellow squares is a mixture of black oil from the Jurassic and gas condensate from subsalt Silurian. Okay, so conclusions for stable isotopes. Stable isotope ratios are only weakly related to source rock age. Their main strength, of course, is for correlation. Whole oil carbon isotopes, Sofer plots, Galimov plots, those isotope type curves, they're useful for correlation. You can use the Sofer canonical variable to indicate terrigenous versus marine input. And you can use the more advanced isotope methods. Of course, they're more expensive and time consuming, but compound specific isotope analysis, that's isotope ratio monitoring, GCMS. Compound specific isotope analysis allows correlation of condensate and light oil. So you can correlate a condensate or light oil with a black oil using those techniques for that molecular weight range. Okay, so here's some references on stable carbon isotopes. I won't dwell on those. If you want to look those up, you're perfectly welcome. And that basically, again, is a very short look at the references to try to minimize the time that we spend here, make this a short lecture. I want to talk about biomarkers now. These are molecular fossils, and we can use them to identify petroleum systems, many times even when the crude oil has undergone extensive secondary processes like biodegradation. These are resistant compounds to biodegradation. So here's a fossil and hand specimen under the microscope. Yeah, we saw some humanite. We can see the cellular structure. And if you use a gas chromatography and mass spectrometry, a GCMS spec, you can actually see individual biomarkers. And I showed you this structure before. This is one of those saturated naphthenic compounds. It's called cholestane. It's got 27 carbon atoms in it. And we know where it comes from. We know it comes from cholesterol in living organisms. And yeah, we can go and look at that. This describes some of the advantages of biomarker analysis. Correlation, good for correlation of oils and source rocks. The biomarkers actually also tell us about source rock lithology, depositional environment, redox, and organic matter input. We can use biomarkers, especially the stereoisomers, for thermal maturation and basin models. We can use them to predict or show the extent of biodegradation and predict physical properties. We can even use them for reservoir continuity, as you would use capillary GC. And some biomarkers even have age significance because they're coming from organisms that lived at specific times during the geologic past. So I'll give you a quick example of some of these. This is our cholesterol story. All eukaryotic organisms contain sterols, right? They're absent in archaea. They're absent in eubacteria, right? but they're abundant. This doesn't look like a big number. Eukaryotes generally contain 0.01 to 0.1 weight percent sterols, but that actually is a big number. The sort of average 150-pound man is going to contain about 300 grams of milligrams of cholesterol, right? So this is cholesterol. That's the stuff, the bad stuff that ends up in your arteries if you eat too much fatty food. During diagenesis, that hydroxyl group is removed as water, and this double bond is saturated, and we have the same backbone structure that we had in the original cholesterol. Why are the sterols so important and so abundant? Well, if you look at eukaryotes, this is a eukaryotic cell. You can see it has a lipid bilayer as the cell membrane, and there's a lipid bilayer in the nuclear membrane that contains the genetic material. So here we have Golgi apparatus and mitochondria and so forth. But if you blow this up or blow that up, you're actually looking at a bilayer. And these are amazing. A bilayer would have phospholipids in it, yeah, big long chain phosphate groups with long chain alkanes attached to them. And that's where a lot of the alkanes come from in crude oil. But also the sterols here. I'm showing the polar head of the sterol. That would be the end of it that has the hydroxyl group. And that is, like dissolves like. So the OH group is going to face the interior of the cell, which is mostly water, the cytoplasm. Or, and the other part of the bilayer, it's going to face the exterior of the cell, which is also mostly water. And this thing will self-assemble, basically. The apolar or non-polar ends face each other. So this is a bilayer, and it protects the cell and keeps it intact. Sterols are also very difficult to biodegrade, and that's one of the functions they serve here as membrane components. They protect the cell from attack by other organisms because it's very difficult for them to degrade these sterols. They're polycyclic compounds that are hard to degrade. Here's cholesterol. You can see there's that polar head, and there's the apolar tail. It's about 19 angstroms long. Right, that's cholesterol. Well, there's an analog to this in the bacteria. This is bacteriohopane tetrol, and that is a major cell membrane component there. In this case, the polar head is actually along the side chain, this long side chain, and this has 5. It's a pentacyclic triterpane instead of a tetracyclic, but it performs pretty much the same structure, the same function. The structure will look a little bit different. And what you actually see is if you go to the eukaryotes, this is the one portion of that membrane. Here's your polar head on the phospholipid, and there are those long chain alkanes on the phospholipid. And then right next to it, the polar side is the OH group on the sterol. And they fall in like this, they hang like that inside that half of the membrane that we're looking at, the polar head and the more fluid region, and the sterol, sort of stiffens the membrane and helps protect it from attack. The same thing in the eubacteria, the prokaryotes, except now the polar part of it is this side chain. So these compounds survive in the sediment after the cell breaks apart when the organism dies, and they're very difficult. They still perform the same function. The microbes aren't very good at attacking a real complex structure like this. They can chew right down the alkane chain here, but attacking ring systems is very difficult in terms of biodegradation. So how do we detect the products in oils and in rock extracts? Here is a GCMS system. It's got a chromatograph, but instead of a flame ionization, it's got an ion source here. And this basically breaks apart the peaks, the molecules as they come out, breaks them into ions and accelerates those ions down what's called a quadrupole. So the quadrupole analyzer can be focused, right, using RF and DC current. It can be focused on specific masses of ions, and then you monitor those. So you have an electronics multiplier here to monitor those ions as they come through. Of course, there are a lot of ions generated, so you also need a computer. But GCMS, just straight desktop GCMS, is a workhorse that involves some pretty sophisticated ionization and analysis using a quadrupole. So this is what happens. You have in the ion source, you've got a filament, and you take that molecule, and you excite it with high energy electrons from the filament, and you break off a molecular ion. This has the same molecular weight as the parent molecule, yeah, and it's now charged. So the electrons, by thermoionic emission, are concentrated into a beam, and you accelerate those. Then perpendicular to the beam here, you have a high energy electrons ionize analyte producing radical ions, which are directed toward the mass analyzer by a repeller electrode. So this is repelling those ions down the flight tube. And this is kind of the key behind the analysis. We use for the electron source, we use 70 electron volts. This is just sort of a graph of the stability of different carbon-carbon bonds to different voltages, different electron voltages. And you see why most GCMS systems use 70 electron volts in their ion source, because it's the best for breaking these bonds apart. So what we do is we break up stearins, we break up terpenes. Here's a stearine, X being continuation of the side chain in each case. This is something that came from a eukaryote. This is something that probably came from bacteria. And now we ionize these things. And what we do is we generate characteristic fragments. Of course, you generate lots of fragments. You know, you can generate a methyl fragment here by breaking that methyl group off. Or you can generate all kinds of little fragments, but there's a dominant fragment that's produced. You can see it tends to break right across this 5-membered ring. This 5-membered ring is strained. So that tends to break right there. And this ion right here has a mass to charge of 217. So it has a mass of 217 and a charge of 1. Okay? A terpene, they tend to break here and give 191, a mass to charge 191. So you will see stearine mass chromatograms of M over Z 217 and M over Z 191 used to monitor all the stearins, because the length of this side chain means you're going to get different stearins coming out of the GC. So this is not a mass chromatogram, this is a mass spectrum of cholestane. And you can see there are lots of ions formed. We've got that electron multiplier measuring those, and we've got a computer to record them. And you can see here is that what we call the base peak. Lots of response at 217, that's the base peak. But you know, then we get all these other ions. This is the molecular ion, molecular ion. And then here's a methyl group down here, and then there are other groups that can be broken off of this. So we have an M over Z 217. If we monitor 217, we're going to only see stearins. And this, you'll probably never see another one of these. These are mass spectra. They're used to actually identify which particular compound you're looking at. So in this figure, I'm showing you a normal GC run for an oil. There's our pristane and our phytane, yeah. And now if we look at the GCMS results are sort of the grass between these trees here. These are the big alkanes. Here's NC27. And all those little red peaks down in there are represented here by that red. And if we look at stearins, M over Z 217, look at all the stearins coming out. Of course, these are lighter than those because they're going through the GC faster. And the same here, we've got terpenes, all kinds of different terpenes coming through, lighter terpenes, heavier terpenes, and we can measure them with high degree of accuracy. So let's look at a GCMS trace for stearins. This is now M over Z 217. okay? And you see it's pretty complicated. This is the GC time, right? When it elutes from the gas chromatograph, and now we've got all these peaks. Well, we've got C27 sterings. Here, C26 sterings. See here, the C27s. Notice there are multiple C27 sterings with slightly different structures. C28, C29, C30. And you see some repeated things in here like that doublet you see. And those are basically different carbon numbers, but they're all sterines because we're talking about M over Z 217. This is a little complicated. A lot of desktop GCMS analyses are done, and you can get 95% of the way there in terms of interpretation sources for oils using straight GCMS. But a lot of people now are using GCMSMS. And I'm going into this detail so you don't have to worry about it in the future. If somebody says, hey, this is GCMS, but this data over here is GCMSMS, you know the difference. This is GCMSMS. So some people would call this a triple quad. You see the triple quadrupoles here. So we have an ion source that's breaking the ions out from the compounds as they come through. Some are sterines, some are terpenes. We've got all kinds of compounds coming through here. We focus using an analyzer. We focus on the molecular ion that we want to see. Then in the collision chamber, that molecular ion breaks apart to other ions. And then in the analyzer, we focus on the daughter ions that we want to see. So we can exclusively look at sterines, or we can exclusively look at terpenes of a given carbon number using this approach. This is really powerful technology, and this just shows you an example of it. Here we have, this is a standard right here, but here is the C26 sterines. You can see there are a whole series of them coming through here. And this is now GCMSMS, where we focus in the first quadrupole on the molecular ion, right, which is, you know, this mass. And then we look at M over Z 217 in the third quadrupole after those molecular ions have broken apart. We focus on the 217, so it has to be a sterine, but it has to be a sterine with that molecular mass. So these are C26, these are C27, these are C28, 29, and 30. Well, if you put those all together, that would be your GCMS run, and you can see how there would be interference. They would interfere with each other. Again, this is a standard that's used. Okay, how is that data actually used? Well, one way to use that GCMSMS data is in a ternary diagram. This is an example from a long time ago. I was working for Chevron in the North Sea, and they had oil from Piper. Remember, there was a platform called the Piper platform. They had a rock, the Kimmeridge source rock, that they wanted to look at. And they knew that Piper oil came from Kimmeridge source rock, but they also found an Eocene oil that was biodegraded. It was fairly low API gravity, and from GC you couldn't do a correlation from GC because of the biodegradation. They said, are they related? Well, we ran the GCMS of the biomarkers. Remember, these compounds are very resistant to biodegradation. So we knew that the Eocene oil had not been biodegraded to the point where the sterines were altered. We ran the samples, and you know the error bar on the measurement here is about the size of the point. So this is a correlation. This is a correlation, oil-oil correlation, and also oil source rock correlation. Here's another example of GCMSMS data. This is some work that we did. Again, this was done at Chevron. This is, again, a fingerprint, basically, we're looking at. This was some work that we did for the Russians. Alexei Kontorovich came to us and said, well, there are all these arguments about where the oil is coming from in West Siberia. Some people think it's Precambrian. Some people think it comes from sandstone instead of source rock. You know, what is the origin of this? So we analyzed probably 40 or 50 oils, and we ended up with a ternary diagram like this. We also analyzed source rock from the Bajanov formation, thermally mature in this case, thermally mature source rock that we ground up and extracted and analyzed the bitumen. You can see here we've got both an oil and oil source rock correlation. So we're correlating these oils with each other and also with the Baugenois source rock. These are all Upper Jurassic sourced oils. But we found a distinct group of oils down here, a little more widely spaced in terms of their composition, more C29 styrene, probably because they had more terrigenous organic matter in them. We believe from the biomarkers, we were able to determine that these came from the Tuyaman formation, which is younger. It's sort of lower to middle Jurassic. And we later proved that by extracting rock samples that were provided. So we have really two functioning petroleum systems in this basin. We found no evidence of Precambrian oil in West Siberia. Well, this is an important figure to keep in mind when you look at correlation data. Biodegradation can certainly interfere with correlations. Remember I showed you those gas chromatograms where the N-alkanes were gone, the isoprenoids were gone. Well, this shows the extent of destruction of each compound class. You can see they show variable resistance to biodegradation. This is a very non-linear scale here. It's a 1 to 10 scale. It's kind of like Mohs hardness scale. Remember Mohs hardness scale? Talc is softer certainly than corundum. And corundum is a lot softer than diamond. So it's a non-linear scale. There's a big jump here between biodegradation of the isoprenoids and getting into the steranes here at a 6. That's heavy biodegradation. Most oils are up in here. And I've, in my entire career, I've maybe seen half a dozen or maybe a dozen samples that get down in here to the 9 or even 10 range. These are really rare. These are extremely stable compounds. So you can do your correlation with steranes, do GCMS or GCMSMS on the steranes. And unless you have heavy biodegradation, which you can recognize if you look at the mass chromatograms, 217 mass chromatograms, you can recognize that. But if it's not up there, you can still do a correlation with steranes. But if it is biodegraded, then you can look at other compounds. You can go ahead and look at diasterenes. These are rearranged steranes, and they're much, much more resistant to biodegradation. This is again a GCMSMS showing. I've circled sort of the diasterenes here. You can see sort of a doublet. Here's actually four peaks here. I had a student one time say, well, why are there 4 peaks there and only 2 here and only 2 there? And this is one of the wonderful things about teaching students. The student got me thinking, and I said, well, you know what? There are multiple peaks under these guys. And we went and synthesized some compounds and co-injected our laboratory synthesized compounds. And we used a least squares regression of quantum chemical descriptors like the molar volume and torsion angles and surface area from molecular modeling to actually determine the elution order of these compounds. So we identified these 4 compounds right here, which are they're actually present up here. They're just co-eluting, right? They're just co-eluting. Anyway, the diasterenes are present in clay-rich rocks, and we use those diasterenes on the same samples from West Siberia. And if we had a sample that didn't have steranes in it, we could use the diasterenes. Notice the methyl groups here are now down here. And we still have the same story. We have a very nice story. And you can get this diasterene data from the same GCMS run that you get the sterane data from. Here's another example of a ternary diagram. These are monoaromatic steroids. You have to use a different mass to charge ratio to monitor these. Yeah, 256. And this is a plot of those same oils and that rock extract from the North Sea. And you can see again, we're getting more and more information that confirms these correlations. The isotopes agree, the other biomarkers agree that these are all related. So we did multiple analyses to prove that genetic relationship. Unfortunately, some papers in the literature will do 1 cross plot or a couple 3 cross plots of X against Y, and they'll make conclusions about correlations based on that. And that's very dangerous. That you want to be able to look at enough parameters, preferably enough parameters that you can do some chemometrics to prove a genetic relationship. XY plots can be very deceptive. You can have oils that are totally different that plot with the same carbon isotope and the same pristine to phytane ratio. Okay, enough said there. So here's an exercise. These are stearine data and for a number of oils and a seep sample. The seep sample is pretty heavily biodegraded, but the stearines are not altered. And we also have monoaromatic steroid data, okay? And we also have isotope data. So I think you can look at this right away and say, gee, the stearines say that seep is related to these oils and all these oils are related. That also says the same thing here in the monoaromatic steroids. Yeah, they're very similar, very similar. And the isotope compositions are very heavy. These are isotopically very enriched in carbon-13. Well, it turns out these are all myosin Monterey oils. And that's a seep, has a very low API gravity, partly because of the biodegradation. Well, we can do other things with biomarkers, especially when we have GCMSMS. And oil from tertiary source rock has a lot of oleanane. This is oleanane right here, the structure. You can see it's going to have a 191 fragment, base peak at 191 when it breaks across here. Where does oleanane come from? Well, it comes from flowering plants. This is the oleander tree, has these sort of blade-like green leaves, and of course, green. These angiosperms or flowering plants sort of originated back in the Cretaceous, but they really didn't start taking over the land masses until we got into the late Cretaceous and into the Tertiary. So this is the number of families from palynology plotted up. This is from a paper by Mike Muldown and others. We've also plotted on here the oleanane to oleanane plus hopane ratio for oils and extracts. And by and large, there are a lot more bars on here than I show. These are the uncertainties in the age of the source rock for each of these oils. But you can see if you have an oleanane to oleanane plus hopane ratio greater than 20%, it's pretty certain that you've got a tertiary source rock there. So this is an age-related or age-diagnostic biomarker ratio. Oleanane, of course, it doesn't work both ways. If you have an oil sample that doesn't have oleanane in it, that doesn't mean it couldn't be tertiary, and simply the source rock was far removed from input from angiosperms or flowering plants. That's possible. But if it has high oleanane, like up here, boy, that's a tertiary sourced oil. Now, there are a whole collection of these parameters that can be used, and I don't expect any basin modeler to be familiar with all of these, but there are textbooks that you can go to and look these up if you need to, and these are just some of those parameters and the references that go with them. This is from the Biomarker Guide, and it shows, here's some marine markers. Here's the 24 N-propylcholestanes, 24 N-propylcholestanes. That's a good marine crucified algal indicator. Here's some leucosterin indicators, beta carotene, right? We talked about batracocaine a little bit earlier. Higher plant indicators, there's oleanane, yeah. And hypersalinity indicators, yeah. Lots of gamasserine, for example, very low pristine phytane. Anoxic conditions, lots of parameters there, right? Carbonate versus shale. So you can say something even about the lithology of the source rock if you have a good geochemist looking at the geochemistry of the oil. Okay, so let's talk a little bit about looking at all of these parameters now at the same time. How similar are two samples? This is an XY plot. We're living in flatland right now, and some papers, some geochemists, that's all they can do is plot X against Y. And again, that's dangerous. Here we have two samples. How similar are those samples? Okay, so one way you could get at that is to calculate the distance between those samples. in 2 dimensions, right? And there's the equation. That's basically the old Pythagorean theorem, isn't it? X squared plus y squared equals z squared. Z is the square root of x squared plus y squared. Well, we can do that with ascendant hierarchical cluster analysis or hierarchical cluster analysis. And we can plot this up. Let's do this. Let's measure this for a number of samples now. Here's a simple example with 2 measurements on 7 different samples, okay? So what are the 2 most closely related samples here? This is a little chemometrics here, basically multivariate statistics. Well, there they are. So we can measure that distance, right? We have X and Y. We know what Z is then. And the next 2, and the next 2, and the next 2. Yep, and we've sort of got 2 groups here, don't we? And then there with those 2. And then this one in the lower left is a bit of an outlier, isn't it? So that's, there's that cluster distance. And we can plot this. I have this, I say, ascendant hierarchical cluster analysis. You could also say hierarchical cluster analysis, where the cluster distance, this distance to the tie line here, is the measure that we've made. Okay, so that's a HCA dendrogram where the cluster distance is telling you, you know, I've got differences in the samples here. These 2 are closely related, and that one, number 4, is similar. And then there's this sort of little group. We could put a similarity line right down here and say we've got 3 families. These 3, those 3, and then this one would be the 3rd family. Well, you can do this for multiple parameters. Yeah, multiple parameters, not just 2. You can do it for multiple parameters. This is a cluster, an HCA that I did many years ago in the Gulf of Mexico. And at the time, this was, you know, we were quite interested and quite amazed at the result we got. There were subsequent publications which basically confirmed this. This is a cluster diagram now for several hundred samples of oil. And you can see I've put a similarity line here to break these up, and the cluster distances are here. And there are big cluster distances between some of these groups. Here, these oils we know are from the Wilcox Formation, the tertiary. Here's another tertiary group. Here's some Cretaceous oils. And here's some mixed oils, Tithonian and Oxfordian. These are mostly down toward Mexico. And here's the Napo La Luna oils. So we had multiple families, and where you put this similarity line is kind of up to you as an interpreter. But of course, there are statistical ways to look at the validity of how far you can put this over to the left. You want to start off by making it simple and just looking at major groups. So how do you do that? Principal component analysis. That's now another step above hierarchical cluster analysis. That's just more rigorous than hierarchical cluster analysis from a statistical standpoint. You find new coordinate axes that are oriented to span the maximum variation in the data. You project those then, multidimensional data onto these new axes, and then you separate those axes that correspond to information from those that are noise. So here we have this is a principal component diagram. And I guess I'm not going to be able to rotate that for you. Yes, I am. Okay, that's going to rotate. So this is for a series of oils from the Circumarctic. There's hundreds of oils here. And you can see this is from all the way from Russia to Alaska, all the way around the Circumarctic, north of 55 degrees. And this is summarized in a paper in 2007. And you can see very clearly here that we have distinct groups. There's still some overlap between the blue and the green, but we have distinct groups based on principal component analysis. And in this case, we were looking at more than 20 different source-related geochemical parameters. These were mostly isotope ratios and homolog ratios, like the oleanane to hopane ratio, right? So this orange group right here, most of these, virtually all of these have oleanane in them. So they're young oils. Some of these others, like the red group here, these are actually Precambrian oils. Okay? So we can we can do that kind of analysis, and it's really very powerful way of looking at the data. So here's some of the data from that study. I've changed the color scheme a little bit here, but here's some of the families that we defined in that study. And you can see here, there's kind of a trend here. All these over here on the barrel arch, this to the west, are sort of in family 222, the Triassic Schublick marine carbonate source rock based on the biomarker composition. And then we have some oils here that are more Jurassic Kingak sourced oils. Yeah, we've got some others in here. These are unusual Schublick oils. And then all of these oils right here, the box, these are from Prudhoe Bay, which is the biggest field on the north slope of Alaska, probably 19 or 20 billion barrels reserve. So can chemometrics deconvolute those mixtures? Yeah, we can do that. We can use alternating least squares of concentrations of compounds, not ratios. Ratios mix as curves, right? So we're going to use concentrations of compounds in the range of C15 to about C35. And this is arranged, this figure is arranged from sort of southeast to northwest. And this is Prudhoe Bay. It's a nonlinear scale here, so I've got a lot of samples from Prudhoe Bay. You can see in the west, out here, these oils are dominantly Schublick oils. They're coming from the Triassic. Whereas in the east, here, these are Hugh gamma ray zone oils. Yeah, the green. And now there's a third source. We can deconvolute mixtures, 3 or 2 or 4 if you want. But here we're deconvoluting 3, and you can see the Kingak shale is sort of a bystander. It's not doing the big mixing here. It's the Schublick mixed with the Hugh gamma ray zone. Schublick is dominantly a sort of a carbonate source. Hugh gamma ray zone is more of a shaly source of different age. And this is all summarized in this paper in 2008, where I talk about how to deconvolute mixed crude oils. And unfortunately, people still try to deconvolute crude oils. You see it all the time in the literature using ratios, and their answers are frankly wrong. So this is an approach, and we compare the results with using ratios. So how does that story jibe with what you see in the field? This is part of our three-dimensional, this was a Petromog model of the North Slope. And this is your cross section. And you can see our oil types here, Schublick oils. Here's the Prudhoe Bay field, which is mostly in the Ivishak here. And this is the mix. Basically, what it looks like is at Prudhoe Bay, underneath this unconformity, this is the lower Cretaceous unconformity, we have mixing of these Schublick oils with Hugh gamma ray zone oils. So the model, we can back the model up in time, and basically this is what the model looked like in the early Eocene. At that time, the Schublick formation, which is right here, and you can see the Schublick here, was thermally mature because this is like a giant tilting set of sediments here. The Schublick was thermally mature and generated hydrocarbons that migrated up dip into the Kuparuk River and also into the Ivishak sand here. And they were trapped underneath lower Cretaceous unconformity here at Prudhoe Bay. Later, of course, this whole thing tilted toward present day, and now the Schublick has been uplifted, and the Hugh gamma ray zone, which is immediately above the unconformity, became mature. And of course, an unconformity in many cases is an ideal migration path. So the Hugh gamma ray zone oil is migrating up here and mixing with Schublick oil in the Ivishak reservoirs at Prudhoe Bay. And that was written up in this paper in 2007. Well, here are some conclusions on source and age-related parameters. You may not be an expert in this now, but I think you Having listened to this, you have a better feel for the validity of the data that you may be looking at or the paper that you may be looking at. We're looking at homolog ratios like C28 to C29 steranes, for example. Homolog ratios are useful for correlation. We use stereoisomer ratios for thermal maturity, and I haven't lectured about those here, but stereoisomer ratios are discussed in detail in the biomarker guide. Of course, biodegradation can alter correlation parameters, so before the correlation is done, you always want to rank the samples in terms of their level of biodegradation before you attempt correlation. There are many studies in the literature where they haven't done this and they see no correlation. Well, it's because the sample, one of them is biodegraded and the other one isn't. You want to confirm the in situ origin of the source rock bitumen. So if you extract bitumen from a source rock, you want to make sure that source rock is not fractured or that contains oil-based mud or other contaminants. You want it to be indigenous, and there are ways of doing that. Biomarkers can specify source rock age, depositional setting, lithology, organic matter input, bacterial, algal, archaeal, whatever, and redox conditions, oxidity. This means that a good geochemist, if you give them an oil sample, a good oil sample, they should be able to tell you what the source rock was like. They may even be able to tell you something about the age. Okay. Chemometrics, we went through that very quickly. I've published a number of papers on chemometrics. It is a very powerful tool. Many geologists shy away from it because they're worried about the mathematics, but it works very well and it's a tool that should be used. Multivariate data analysis. Correlations apply only to the range of compounds used in the analysis, so be very careful about that. I'm going to talk about that next at the end of this lecture. So here are some references for tracing the origins of crude oils. You see I like doing that, so I've got a bunch of papers that do that, and there are many more, but I try to boil it down to some that might be of interest to you. Okay, so let's talk about mixtures and deconvoluting mixtures. We talked a little bit about that when we were talking about actually physically mixing oils to identify reservoir continuity, some of the work of Rong Wang and Russ Kaufman earlier. So here's the question. What if you're mixing not just two black oils, but what if you're mixing black oil with a condensate, a gas condensate? That's going to be problematic. What's the impact of mixed light oil and heavy petroleum on fluid source assignment, like a hierarchical cluster analysis, and predicted gas to liquid ratio? I'm going to use GLR instead of GOR here because I want to include in the liquid gas condensate. Okay. Biomarker concentrations for 4 pairs of petroleum fluids having end-member GLRs from 100 to 50,000 standard cubic feet per barrel were mathematically mixed in 5% increments. So we actually didn't mix these in the lab. We mixed the end-member compositions using parts per million. That requires internal standards. Yeah, we had parts per million concentrations for a whole selection of compounds throughout a broad molecular weight range. And then we mixed those together mathematically. So there's no issues here with not weighing the sample properly or evaporation of the oil. Right, it's just mixing the raw data. Each series of mixtures, we got 4 pairs, was evaluated for genetic affinity by hierarchical cluster analysis, the standard sort of approach that I like to use, and for source allocation by alternating least squares regression of compound ratios, ALSR, and concentrations. We're going to contrast those two. Here are the 17 independent source-related variables that I used in this study. And again, we're not mixing them physically, we're mixing them mathematically. Here are the ratios, pristane phytane. Here's some terpene ratios and some propane ratios and sterane ratios, diasterane ratios, oleanane ratios. So we're going to use that for looking at ratios. Here are the 4 mixtures, and this is a little bit of a preview of a talk that I will give, I hope to give, at the APG in Houston, although I think our meeting may be canceled because of the coronavirus. but this paper has been submitted to APG Bulletin. And this shows this pair right here, number 2, is the one we're going to talk about. We're mixing a self-Viking graben with a high gas-liquid ratio of 12,600. That makes it a gas condensate. And we're mixing the other end member. This is another source. This is an oil source with a GLR of 1,000. So this would be described as a black oil. GORs, or gas-liquid ratios, less than 1,000, we'll call that, less than 3,000, we'll call that black oil. Between 2,000 and 3,000, you might want to call that a volatile oil. And greater than 3,000, those are gas condensates. Okay. So this actually is the Dropney sourced oil. Sorry, this is the Dropney sourced oil right here, which is Upper Jurassic. And this is another source, the Schleipner-Huygens, which is a terrigenous dominated source. And the 11.8 here is the ratio of those two GLRs. Okay, so this is a figure from Chris Cornford's paper in 2018. And I actually gave this to you as a little homework assignment to think about. We're going to talk about it again now. How do you explain the apparent absence of the coal gas, even though we can see in geochemical logs, we can see there's good material here, high, pretty high TOCs, relatively good TOCs. The hydrogen indices are not, they're not typically over 300, but here in the Dropney, that's a Kimmeridge equivalent. So the hydrogen indices are 300 to 600 or more. And this is a gas prone, but you don't really see it. And there are people that ask the question, where did all the coal gas go? Richard Patience from Chevron published a paper on this a few years ago. It must be there somewhere. Where is it? We don't see that SVG gas in the geochemistry that we do. So this is hierarchical cluster analysis using those ratios that I showed you in the previous slide. And it's very interesting. You see most of the samples, these mathematically mixed samples, plot together as if they're genetically one family. We're going to call that the Dropney subfamily. I put my similarity line here, and these are the other mixtures that we had in this study. And there's some spreading out of them here that actually is systematic. But the other end, the other extreme here is just one sample. That's the sample GIT, which is the Schleipner-Huygens gas condensate. So that says that a lot of the mixtures here are actually dominated by Schleipner-Huygens, but they look like Dropney oil. Okay? There are a lot of papers published on the self-Viking graben, and they don't see this. So here's a table. It's kind of a complex table. What I've done is I've gone to that cluster analysis, and I've blown it up. I've left the GIT off. That's that very big cluster distance down to its own little family. And now we have the Dropney family here. And you can see it's very systematic. The green ones here, characterized by GQB here, that sample, 100% Dropney oil, SVG oil. Okay, it's right there. And it forms a tight little group here, 85 to 100% SVG oil. And there are those 5% mixtures I told you about, the mathematical mixtures. And yeah, here's 65 to 80% Dropney oil here. That's the green ones. This clear ones right here, the white ones, characterized by GZI. There's GZI. These guys, now we're starting to get significant amounts of SVG gas here. This is 60 to 75%. It's dominated by the gas input, but it's clustering at the scale we looked at earlier with the Dropney oil. Okay, well, that's a serious thing to keep in mind. You can see it's very systematic here. This little group has a little bit bigger cluster distance, but PXM here, right there, that's 80 to 95% SVG gas, just a little bit of the Dropney oil in there. And of course, GIT is 100% of the Schleipner-Huygens. So I think what this is saying is you can completely miss, in terms of classifying with hierarchical cluster analysis, you can completely miss the story unless you recognize that gas fraction of the oil. And you got to be careful about what range of hydrocarbons you're talking about when you do your mix. We can also deconvolute these mixtures using different approaches. Here's ALSR, alternate least squares of ratios, alternate least squares based on a whole liquid basis, which is basically C6 plus, and alternate least squares of concentrations on a whole fluid basis where we account for that gas fraction. So it's C1 to C, 35 plus. Look what happens. Here is an example right here, PXM. The mix, the mathematical mix, that's actually the true mix of SVG gas. 10% SVG gas, 10% SVG oil, 90% gas. If you use ratios, if you break apart those, if you use those ratios I showed you earlier in the figure, one of the earlier figures, it only estimates 8% SVG gas, where there's 90% there. It thinks there's 92% oil there. That's deconvoluting using the ratios. If you use concentrations on a whole liquid basis, yeah, you're coming closer to the answer. But again, you're ignoring that gas fraction. If you include the gas fraction by doing some mass balance calculations, and we show how to do that in the paper, we get right on the correct allocation of those different sources. This is something that people have not recognized in the past, and I think it probably explains the question, where did all the coal gas go? So this is kind of a summary of what I just showed you. Here is the mathematical mix. This is the mass of the SVG gas source. And here's the ALS mass that's calculated. So the mathematical mix matches perfectly with the calculated concentrations on a whole fluid basis. If you look at whole liquid concentration, that's not from C1, that's from C6. You're not accounting for that gas fraction, and your estimates are going to be off. And it gets even worse if you use compound ratios in your alternating least squares. And if you use ratios, like most people in the virtually everybody in the literature up to this point, they're going to severely underestimate the SVG gas contribution to the oil. And that also is going to affect the GLR, right? The gas liquid ratio. Okay. So this is something to keep in mind. If you look at the isotopes, Patience was looking at isotopes, you see a very similar effect there. Here is the isotope composition of the oil, SVG oil end member. Here's the SVG gas end member. But look what happens here. We're mixing now, increasing SVG gas. It's a kind of a flat curve here. It doesn't really change much from -30 to -29.5 or so, -29, up to about 70, 80% SVG gas. You don't really see it. And notice that the curve for GLR is actually increasing at a faster rate than that for the carbon isotopes. So you will seriously underestimate the gas liquid ratio based on your isotope geochemistry alone, because you're not seeing that mix. Okay, so here's some conclusions for binary mixtures of petroleum. HCA of compound ratios identifies genetic fluid families through a range of molecular weight. As long as you specify that weight range, you're okay. But it can be misleading for mixtures of end members with distinct compound concentrations or gas liquid ratios. ALSR can deconvolute oil-oil mixtures having similar GLRs, but mixtures having different gas liquid ratios, compound ratios, and concentrations mix in a strongly nonlinear fashion. ALSR fails to deconvolute mixtures of oil and gas condensate. It underestimates the gas liquid ratio and the contribution from the gas condensate. ALSC deconvolutes mixtures, 2 or more end members. We just did it with 2, but GCMS quantification requires internal standards. So that's why a lot of the analyses you see in the literature are done with ratios. They didn't go to the trouble of co-injecting internal standards with their samples so they could get at ppms. They have to use ratios. So ALSC, concentrations of whole fluid, is more accurate than ALSC of whole liquid, C15+. Many interpreters use ALSR to deconvolute mixtures, thus yielding inaccurate results. I had a discussion one time at an open meeting, as was at the Hedberg meeting a couple of years ago, where one of my colleagues, I made the statement, well, you better be using ratios. And my colleague said, no, we're using ratios and it works just fine. It's highly repeatable. And so I've included this figure for the benefit of my colleague there. This is highly repeatable right here, but it's the wrong answer. So you want to use ALSC of concentrations to deconvolute mixtures. Okay, so here are the selected references for petroleum mixtures. As I indicated, the paper that we were talking about has been submitted to APG Bulletin, and it should come out hopefully this year. Here's the paper by Richard Patience that you might want to look at. Here's an earlier paper where I discussed deconvoluting mixed crude oil using concentrations rather than ratios. And there's some other papers in here you might want to look at for comparison. All right, well, that pretty much concludes what I want to say about geochemical correlation. I know that was a lot to talk about in one day, but again, I think it's something that basin modelers should not ignore. You want to be as sure as you can about the source rocks in your basin, and to do that, you need good geochemical correlations with the oils. In the next lecture, we're going to talk about gas geochemistry. That includes a tremendous amount of material. Also, one of the things I definitely want to talk about is biogenic gas generation. I think a lot of the software out there, especially basin modeling software, could do a lot better. But we will leave that for that discussion. I would like you to think about the following slide before we get to the next lecture. This is actually from Petromod, and this shows some of the primary reactions that you can use to model biogenic gas generation: Gaussian distribution, constant rate, and Middleburg. And you might just want to think about those approaches to modeling biogenic gas. I will talk about those three generation methods in detail then. So I look forward to giving the sixth and final lecture, and I hope you can join me for that. And thanks very much